this video, we will apply our old model for the spring and damper assembly to a new application, an automobile suspension system. There are no new models here or any new theory, but this project is a good programming exercise, and it's a good example of the kind of careful geometric reasoning that is part of engineering. The diagram shows a 2D car with a spring damper assembly at each axle. The car body is represented by a rod of length WB, the wheelbase, or the distance between the wheels, and has mass M. The forces acting on the car are gravity, acting on the center of mass, and the spring damper assemblies acting at each end of the car. The car will be traveling at a constant velocity, so we don't need to keep track of its horizontal or X position. As the car travels, bumps in the road cause the body to bounce up and down and to rotate. So the state of the auto will be the position, that is the height of the center of mass of the body, and the angle the body makes with horizontal. The function PT is the height of the car's center of mass, and alpha of t is the angle the car makes with the horizontal. The height of the rear of the car, that is above the rear wheel, is P of t minus sine of alpha of t times WB divided by 2. And the height of the front of the car is P of t plus sine of alpha of t times WB divided by 2. As the car travels along the x-axis, the road can have bumps which cause it to bounce up and down. How do we implement the road? We will define a function road of x, which gives the height of the road for a given x coordinate. Here we have a new bit of MATLAB syntax. It's called an anonymous function, and it's defined in line. The syntax is you give the name of the function, an equal sign, and an @ sign, and then the parameter list. In this case, we have one parameter x. Then you write an expression which computes the value of the function. In this case, we have a logical expression that evaluates to 1 when x is between 10 and 11 and evaluates to 0 when it's not, times 0.5, which gives us the bump in the road that we want. Let v be the car's constant velocity. Then v times t is the position of the rear wheel of the car at time t, and v times t plus wb is the position of the front wheel of the car at time t. So we can define the function r sub r of t equals road of v times t, and that's the height of the road above the rear wheel at time t, and r sub f of t equals road of vt plus wb, which is the height of the road beneath the front wheel at time t. Here comes the careful geometric reasoning I was telling you about. Now we will compute the spring and damper forces at the rear and front wheels. Let L be the height of the car when the road and the car are level and the springs are in their relaxed state. That is, when there is no gravity compressing them. In that condition, the position of the rear of the car is L and the position of the front of the car is L. When the rear of the car, i.e. P sub r, goes down, the shock absorber compresses by the amount L minus P sub r. When the road at the rear wheel, i.e. R sub r, comes up, the shock absorber at the rear wheel compresses by the amount R sub r. So the displacement of the rear shock absorber at time t is given by L minus P sub r of t plus R sub r of t. The displacement is positive when the shock absorber is compressed and negative when it is expanded. The upward force the rear spring exerts on the car at time t is k times the displacement of the spring, that is k times L minus P sub r of t plus R sub r of t. The rate of change of the compression expansion of the shock absorber is given by L minus P sub r plus R sub r prime, which is minus P sub r prime plus R sub r prime, and it is positive when the shock absorber is compressing and negative when it is expanding. So the damper force on the rear of the car at time t is C, damping coefficient, times minus P sub r prime plus R sub r prime, and it's positive when the shock absorber is compressing and negative when it is expanding. So, combining these results, we have an expression for the force exerted by the spring damper assembly at the rear of the car, F sub r, which equals the expression shown. So we have expressions for the forces exerted by the spring damper assemblies at the front and rear of the car. The model for the car is P double prime of t equals minus 10, which is the acceleration due to gravity, plus the combination of the spring damper forces from the front and rear of the car divided by m. The torque exerted on the car by the spring assembly at the rear of the car is minus F sub r of t times Wb divided by 2. The negative sign is because a positive upward force at the rear of the car creates a negative torque on the car body. That is a clockwise torque. The torque created by the front spring damper assembly is F sub f of t times Wb divided by 2. The model for the angular acceleration of the car body is given by Newton's second law of motion for rotation and is alpha double prime equals t divided by I. The graphs show the positions, i.e. heights, of the front and rear of the car. The top graph is the height of the front of the car displaced by 3, and the bottom graph is the height of the rear of the car. In the first graph, we started the simulation with a center of mass at a height of L, which is the position of the car when the springs are relaxed. So the springs compressed and begin to settle at a position that would support the car's weight, which turns out to be at a height of 1. In the second simulation, the car started level with the center of mass at position 1, so the springs were in a compressed state just enough to support the weight of the car. The graphs show the response of the front and rear of the car to a bump in the road. The front wheel sees the bump first and both ends of the car start bouncing. Then the rear wheel sees the bump. The assignment is to program the sim and reproduce the graphs in the video.